Hello, my name is Dr. Richardson, and the title of my course is Using Vector Calculus to Solve Problems in Electricity and Magnetism. So my email address is attached. So just for highlights, organizational highlights about the course. Learning is not a passive activity. Watching me write the notes in a lecture for the 12 lectures during the summer is not going to cut it. You have to take notes. Take notes during the lectures. Write as I write. That way, your brain will be hardwired and it'll be easier for you to learn the concepts and problems we go through in the lecture and also figure out those that you're having difficulties with. So simply do not sit back and watch me perform. You have to jump into the swimming pool. Do the problem sets. Do the problem sets individually, without help, without talking to colleagues, without consulting books, without consulting Google or any other search engine. Only by solving the problems will you learn the material in the course. If you do not do the problems and problem set, you're going to get 0 out of this course. You get nothing out of this course. There's no problem with attempting a problem and getting it wrong. In fact, when you look at the solution key to see what you've gotten wrong, you will have learned something. So that's important. And again, some of the problems you'll find be very straightforward. Some may have a little twinkle to them from what examples compared to examples we worked through in lecture. Others you'll have to think about. But when you get the solution key, so you'll get weekly problem sets, they'll do in a week, and then you'll have online access to the solution key. If you come across a problem that you couldn't work and you're looking at the solution key, cover the key with a sheet of paper and just scroll down from the top, see if you can get hints as to where to proceed. Just don't read the solution. You'll learn more that way. Ask questions. There's a recitation section available after lecture from 3:30 to 4. In principle, we can go on to 5. I'm available by email during the weekend, on weekends, by my email address srichards22@comcast.net. So please use it. I promise to get back to you within 24 hours of receipt of your email. Finally, obtain, retrieve, find, or buy a ruler. That's going to be very useful, as you'll see in lecture, and it's going to be very useful in your doing the problem sets. Okay, so let's start. So we are going to review a number of mathematical techniques and ideas and concepts that are going to be critical for our discussion of electricity and magnetism. In fact, we're going to spend probably the first 4 lectures of the course doing the mathematics first before we look at an application in electrostatics. So vector analysis. So let me remind you what vectors are. Vectors are creatures that can be expressed in 2 ways. So you see why my ruler is handy. You can have a geometric representation of a vector. Let's say the vector is V. And I'll draw it this way with respect to the X and Y axis. And this is a geometric representation. Now, there's another way to express a vector, and that's coordinate representation. And again, I need my trusty ruler. And again, it's still the same vector V, but I'm going to take advantage of the fact that this vector V really defines a point in space. So vectors are really points. And that point in space is defined by the numbers or scalars X and Y. So that's a word we've just introduced, scalar. Scalar is defined to be a number. When I draw 3 horizontal lines, that simply means I'm defining something. So that's a definition. So it's important to get some notational agreement out of the way. When I write a vector, I'll use this notation of a half arrow. Why? It's just something I've been accustomed to doing for about 40 years now. Some people will write a vector as an arrow, perfectly reasonable. I just don't happen to do it that way. Psychological quirk on my part. And authors of textbooks and papers will tend to write vectors in boldface, which is obviously hard to do in lecture. So I will use the convention of that's me, I'll use the convention of a half arrow. So what can you do with vectors? Well, one thing you can do with a vector, let's say v, is multiply it by a number or scalar, and the answer will be some new vector, w. And it doesn't matter the order of that multiplication. You can multiply a scalar by a vector to get a vector. You can multiply a vector by a scalar to get a vector. Okay, so that's one interesting property of vectors. Now, I'm tempted to say that another property of vectors, well, even before we go there, you can certainly add vectors. And again, subtraction really is the same thing as addition. It's just that you're adding a positive quantity to a negative quantity. So you can add vectors using the laws of geometry, parallelogram, law of addition. Third thing you can do, or you think you can do, is multiply vectors. And the answer is that you really can't do that. You can't really multiply vectors. What you can do is take a vector v, do something with it regarding another vector w to get an answer. So if I take a vector v and dot it into a vector w, I'll get a scalar or a number. Now, I haven't told you how to do this yet. I will in a minute, but this operation is a definition of what's called the dot product or scalar product of two vectors. Now, we will come back to this point a little bit later in today's lecture. Turns out this is not the only way you can, quote, multiply, end quote, vectors. You can do something different than taking the dot product. You can do what's called performing or evaluating the vector product, and that's or cross product of two vectors. So I'm going to use this symbol dot for dot product or scalar product, and this cross for a vector product or cross product. Now, I haven't told you how to do this operation yet. For that matter, I haven't told you how to take the dot product to two vectors. But suffice it to say that I will show you how to do that subsequently. And when we do that, the answer you'll get will be a vector. Excuse me. So in fact, vector multiplication, again, multiplication in quotes, has two different forms. One is the so-called scalar product, one's a cross product, or dot product, or vector product. And I'll use the terms dot product and scalar product and vector product and cross product interchangeably. So before I make any attempts to go any further, I really have to explain how this works. So I'm going to start with the dot product. So I haven't defined how to, in fact, take the dot product. So I will do that now. Okay. So if I have a vector v, and I want to take its dot product with the same vector v, then I will define 3 horizontal lines, the result of this operation to be this creature, which I'll define in a minute, times this creature, which again I'll define in a minute, times the cosine of theta. We're going to have to define theta in a minute. So first things first, v with these 2 parallel vertical bars is what we call the length or magnitude or norm, all 3 terms are synonymous, of a vector. And you may be used to seeing, rather than a set of double vertical lines for the norm, you may be seeing just a single vertical line. And I'm not going to use that notation because I'm going to reserve that notation for the absolute value. In this case of a scalar. So the only thing that's left for us to do is define what theta is. And theta is going to be the angle between the vector v and, in this case, itself. Okay. So this is a definition. This tells you how to, in fact, take the dot product of 2 vectors or the scalar product of 2 vectors. Why you would want to do that is a different question. But what we're going to do now is just set up the mathematics, the vector analysis. We know how to do this operation. So the next thing we need to pull out of our bag of tricks is the invention of something called a unit vector. So unit vectors are going to be vectors with a specific direction and a norm or length or magnitude of 1 or unity. Hence, that's why we call them unit vectors. So I am going to define a unit vector I hat and a unit vector j hat accordingly. This hat is a carré. That's French for a hat. And you notice that I hat points in a particular direction and it's perpendicular or orthogonal. All these words are synonymous. To the unit vector j hat. So in fact, I could start asking myself, what is the dot product of the unit vector I hat with itself? And actually another way to express these two words, perpendicular orthogonal, is normal. So if I ask myself, what is the dot product of the unit vector I hat with itself? And if I use the previous definition, it's just the magnitude of I hat times the magnitude of I hat times the cosine of the angle between them. And I can evaluate this. By definition, the magnitude of the unit vector is 1. The angle between them is, in fact, 90 degrees. So I have, in this particular problem, similar, misspoke. The angle between I hat and I hat is in fact 0. Those vectors lie on top of each other. So in fact, this last quantity is in fact 1 because the cosine of 0 is 1. I've got off the track a little bit earlier because I was looking at I hat dotted into J hat. Those guys are perpendicular, orthogonal, and normal. We'll get to that in a minute. Similarly, J hat has a dot product, and for the same reasons, its dot product is also 1. So again, the topic here is unit vectors. And so let's bring everybody to the party. My unit vectors are 3 very special vectors. I hat, J hat, K hat. They're defined in this representation, this orientation. And we immediately are making a decision of how to write these unit vectors. And we use it employing something called the right-hand rule. In other words, I put I hat, or I could put J hat here, and I could have put I hat here, but I'm not. The convention I'm going to use is I hat is here, J hat is here, K hat is here. So this is my so-called right-hand rule. So, and now I'm in business. I note that I hat is orthogonal to J hat, J hat is orthogonal to K hat, and I hat is orthogonal to K hat. So I can write down a whole set of rules that these unit vectors must obey. We messed up on this a little bit a few minutes ago, so let's correct this. Using the definition of the dot product of two vectors, I hat dotted with itself is equivalent to J hat dotted with itself, which is equivalent to K hat dotted with itself. And those are 1. But if I ask myself, what is the dot product of I hat with J hat, that's a different story. This is what I was trying to do earlier, and I got myself ahead of the game a bit. The angle between I hat and J hat by this diagram is 90 degrees, and the cosine of pi over 2, or 90 degrees, is in fact 0. So in fact, the dot product of I hat with J hat is the same thing as the dot product of I hat and K hat, which is the same thing as the dot product of J hat with K hat, which is the same thing as the dot product of I hat, or rather J hat with I hat, which is the same as the dot product of K hat with I hat, which is the same thing as the dot product of K hat with J hat. And if you use the definition of the dot product of two vectors, any vectors, particularly they're unit vectors, but this definition is true or applies for unit vectors also, all these guys have to equal 0. So what we have written down are the unit vectors in three-dimensional Cartesian coordinates. Descartes was the gentleman who came up with this idea of Cartesian coordinates. Now, I need to say something about conventions. You will see in other courses, in other books, in your research perhaps, people using the terminology of E hat 1 for I hat, E hat 2 for J hat, E hat 3 for K hat. And that's a perfectly reasonable way to do things. People do it all the time. So I don't want you to be confused if you see that elsewhere. We will, in this course, use that convention, I hat, J hat, K hat, and we will not use E hat 1, E hat 2, E hat 3. Nothing wrong with it. You just have to pick a convention and be consistent with it. The one thing I should point out is that you may ask, well, why is this E hat 1, E hat 2, E hat 3 notation even something you'd even consider? And the answer is that because the subscript can go on forever, whereas here you're limited to the number of letters in the alphabet, I'll let you figure out what that is. You can have a case where you have 4 basis vectors or 4 unit vectors, 5 unit vectors, 6, 7, 8. You're not limited to n, in fact, infinity, an infinite number. So you're not limited to the number of letters in the alphabet. And even though this is not the focus of this course, this is extremely useful in the subject of linear algebra. Okay, so again, let's go back to our vector, which we'll write again in its geometric representation. I think we've been calling this vector V. So let's continue to do that. And so now we're in business because we said that this vector had a coordinate representation where you give me a value, scalar x and a scalar y, I know exactly where that vector is. So this is the x-axis and the y-axis. So why did we go to the trouble of defining these unit vectors? Well, here's why. The unit vectors tell us uniquely the directions that we want to build this vector from. So in fact, this vector V has a component in the I hat direction. We'll call that component V sub x. And it has a component in the J hat direction, and we'll call that component V sub y. And we know by definition the directions of I hat and J hat. Now we know lots of other things. We know how to take the dot product of a vector with itself, and I'll just write down the answer. And so if you go back to this diagram, this distance here is just V sub x. This distance here is just V sub y. And the hypotenuse of this right triangle is just the square root of V sub squared plus v sub y squared. So in fact, a very nifty thing comes out of all of this. If you want to calculate the norm of a vector, you want to take the square root of this thing. That's equivalent to the magnitude of the hypotenuse of that right triangle in the figure. And that's just the square root of the dot product of a vector with itself. Excuse me. So a very, very helpful thing. The norm of a vector can easily be calculated by taking the dot product of a vector with itself and taking the square root. You don't have to go out and actually measure the vector. You could. You could take a ruler, measure the length of this vector v. So you could measure v by taking a ruler. A much more easier, much more analytical way of doing it is just take the vector v. You know its x components and y components, so you can easily calculate this dot product, get an answer, and take its square root. Okay, more vector analysis. And again, this may seem very basic and fundamental to you, it should be, but we're going to use these ideas and extend them to more interesting and perhaps complicated systems. So one of the things you always want to be able to know how to do is to resolve a vector into its components. So what do I mean? Well, we've sort of done this already, but I want to go back to this and flesh this out a little better. So again, my vector v in the geometric representation that's a little sloppy, sorry. So again, first thing I have to do is tell you where I hat and j hat are. So there's my vector v. And there's another thing I'm going to note about this vector, namely it makes an angle of theta. So in STEM, Greek symbols are your friends, theta. And what I want to do now is, with this introduction of this variable theta, I want to resolve this vector v into its components. Namely, I want to know what v sub x and v sub y are. Okay, so a couple of things. You will see me and you'll see other authors in the course, other authors in the course of your studies, writing vectors in terms of the unit vectors one of two ways. Some people choose to write unit vectors first and then the components. Others will write the components first and then the unit vectors. They're both equivalent, okay? And you may ask, well, it just seems to me that it's much more reasonable to write everything in the latter form, not the former. But when we start looking at vector operators like the gradient operator, or the divergence operator, or even Laplacian operator, it's going to make a difference how we write this, for clarity's sake. But let's just say for the moment those two guys are equivalent, which they are. Other thing we're going to point out is this angle theta has a direction. And I'll say more about this later. Angles you may be used to thinking of as scalars. They're not. They actually are vectors. Angles are examples of vectors. Okay, so let's move forth. Clearly, this vector v has a magnitude, norm, or length, so that if I ask myself, the cosine of theta is the adjacent side over the hypotenuse, then this distance here has to be the norm of v times the cosine of theta, and this distance here has to be the norm of v times the sine of theta. So in fact, v, which is I hat v sub x times v sub y, that's writing that vector into its components, that's the same thing as I hat times the norm of v, which is just the magnitude of v, times the cosine of theta, plus j hat times v times the sine of theta. Now, one of the things I want to get you to do in this course is when you get a result that looks new or bizarre or strange to you, see if you can understand it in terms of limiting cases. So what am I talking about? What does this expression do when in fact theta is 0? So when theta is 0, it turns out there's no contribution, plus sign, there's no contribution here, the sign of 0 is 0. So in fact, v hat is I hat times v times the cosine of 0, which is just 1. So this just tells you that your vector v will point entirely along in the I hat direction, entirely on the x-axis, and will have magnitude of v, which makes perfect sense. I leave it to you to prove the other limiting case, what happens when theta is 90 degrees or pi over 2. And that'll show you that in fact this expression for resolving this vector v into its two components is the right way to go about doing this. So again, we have looked at in some detail how to take the dot product or scalar product of two vectors so the way this thing is defined is it only makes sense when you have two vectors. You don't take the dot product of 10 vectors or the dot product of one vector. You have to do it two at a time. How about some observations? Why is this useful? Well, we're going to see lots of applications later on in the course when we're going to need to know what the dot product or scalar product of is of two vectors. That's not the time to figure out how to take a dot product or a scalar product. Now's the time to do it. Another point I will make is that if you have two vectors, or one possible application, so here are two particular applications. If you have two vectors u and v, and the dot product of these two vectors is 0, remember the dot product or scalar product gives you a scalar. That's why it's called a scalar product. And in this case, if in fact you have two vectors v and u that obey this relationship, then it follows that v is perpendicular to u. So that's a very nifty thing to do, to ascertain. V is either perpendicular to u, or normal to u, or orthogonal to u. The other useful thing that I want to discuss now is that the dot product is a very useful creature that will allow you to write down something called the law of cosines. There is similarly a law of sines. I'm not going to discuss that in lecture. not that there's anything wrong with it, but in terms of our applications for electricity and magnetism, this law of cosines is going to be extremely invaluable. And I may leave the law of sines to a proof in a future, or a discussion in a future problem. Okay, so what is the law of cosines? And how can we use the dot product or scalar product to in fact prove it? So imagine I have two vectors. I'll write these two vectors. I'll give them names. I'll call one U and I'll call one V. And I'll write these vectors in a fashion such that they are tail to tail. And the angle between these two vectors I will call theta. So if I use the parallelogram law of addition of vectors, then I can see that this guy, written in this direction, must be U minus V. And to save myself some space in writing things down, let me define that as the vector W. So I ask the question, what is the vector W dotted into itself? Well, I've defined W over here. I know how to take the dot product of two vectors. So let's jump right into it and do it. W is simply that. W again is simply that. And using the definition, of a dot product, this is just U squared plus V squared minus U V times the cosine of theta, where theta is the angle between U and V, where U and V are written so they're tail to tail. And again, since W is U minus V, this thing on the left-hand side is just W squared. So there's no reason to put this in red. So let's make it black. So this is the law of cosines. So let's say what it's telling us in words. It says if you have a vector U and a vector V and an angle between them, and then you invent a new vector W in this form, or if you just have a triangle, where those three lengths are defined, and you know theta, I mean, this does not necessarily have to be let's clean this up a bit. So I'll go back to this if you have my triangle. And it doesn't necessarily have to be a right triangle, but I can define U and V and W in this fashion. Then W squared is just U squared plus V squared minus, and that minus sign is there, it's important, 2 times UV times the cosine of the angle between them. And again, this is another case where this example of, or this idea of using limiting cases to check your work if you come up with a complicated expression and you want to know it's right, that you haven't made a mistake, is ask yourself what happens if theta is pi over 2. Well, in this particular case, if theta is pi over 2, the cosine of pi over 2 is 0. And so what you just get is the Pythagorean theorem for a right triangle. Okay. That's something you know from secondary school. Okay, so that's about everything we're going to do for our discussion of taking the dot product or scalar product of vectors. Now, I said early in the lecture that there was another way to do multiplication in quotes of vectors. So I want to focus on that. So there's a second way to multiply vectors. And again, let me be precise. I want to say multiply in quotes, because this has nothing to do with multiplication of scalars that you're used to from arithmetic. So it turns out that you can take a vector A and another vector B and do something to these two guys. That something will be designated by this X. And because it's an X, what you're doing is taking the cross product or vector product of two vectors. So just as I showed you how to do this for the case of the scalar product or dot product of two vectors, I need to define how to do this for the case of the vector product or the cross product. So again, this is a definition: 3 parallel horizontal lines. This equals the norm of A times the norm of B times the sine of theta, where I have to define what theta is. I'll do that in a minute. But there's something that's missing. The thing that's missing is that this cross product of these two vectors is in fact a vector. And this vector will be designated by the symbol n hat. And this thing will have a name. It'll be called the unit normal vector. Okay. So let's see how all this works. So let me start out with a vector u and a vector v. And I'm going to write these vectors down using the aforementioned right-hand rule. And again, I need my unit vectors to tell me what's going on. So n hat is a vector that has a direction and has a magnitude of 1. The direction of the unit normal vector here is going to be defined using the right-hand rule. Namely, it's orthogonal to the plane defined by the vectors u and v. And in fact, in this case, n hat is simply the same thing as the unit vector k hat. Okay, so if we accept this definition for the moment, And we postpone the idea of whether or not the question of whether or not this actually has any importance. Let's take this thing and run with it. So namely, let us ask ourselves, what do we do if we need to figure out the cross product or vector product of two unit vectors? So we in principle know how to answer this question. We've got everything set up. You have to launch, jump in and do it. So I tend to think geometrically. I tend to think in terms of structures and pictures. I don't easily tend to think in abstract ideas. That's not the way my brain is wired. There are people who fortunately don't have that disability. They look at a problem, they see exactly right into the heart of it, and they pull away all the window dressing, and they see exactly what's going on in terms of an abstract idea. For me, it takes a while to get there. So here are my friends, I hat, J hat, and K hat, again, written in using the right-hand rule. So the question I want to ask myself is, excuse me, what is the cross product of I hat with J hat? What is this guy? Well, a few minutes ago, I wrote down a definition of what you need to do if you want to calculate the cross product of any vectors. In this case, in particular, I'm applying it to unit vectors. It's going to be the norm of I hat times the norm of J hat times the sine of theta. I have to come back to a discussion of theta now. Theta is just going to be the angle between these two vectors. And there's a unit normal vector in hat. Well, the magnitude of I hat is 1, the magnitude of J hat is 1, so this is just 1 times 1. The angle between I hat and J hat is 90 degrees, pi over 2, the sine of 90 degrees is 1. And if I use the right-hand rule, this is just the unit vector in the direction of positive z or k hat. So in fact, I hat crossed into J hat is in fact k hat. I hat crossed into I hat is in fact 0. And that's easy to show because the angle between I hat and I hat is 0. The sine of 0 is 0. So you can write down a whole bunch of interesting facts. It's easy to prove. Namely that these three cross products must all be equal to 0. Excuse me. You can also show maybe I shouldn't have erased this backwards, and maybe I should have started from the beginning and erased forwards, but life is a series of experiments. So we just showed that I hat crossed into J hat was K hat. We did this. I'm not going to do this in lecture, but I want you to do this. I want you to show that J hat crossed into K hat is I hat. I want you to show that K hat crossed into I hat is J hat. While you're at it, I also want you to show that K hat crossed into j hat is minus I hat crossed into k hat is minus j hat, and the sixth and final expression I want you to prove is that j hat crossed into I hat is minus k hat. So I want you to show that these guys are in fact true. Now, there's an interesting fact that you can look at this and you can sort of pull this out, especially if you look at, let's number these guys, 1, 2, well, if you want to number these correctly, I guess this is 1. So let's number these 1, 2, 3, 4, 5, 6. If you look at 1 and 6, you will come up with the following suggestion, that I hat crossed into j hat is minus j hat crossed into I hat. And that turns out not just to be true for unit vectors, it is true for any vectors. If you take the cross product of A with B, you'll get an answer that's equivalent to minus the cross product of B with A. Note, this is extremely important, the dot product does not have any such problem at all. The dot product of two vectors A and B is the same regardless of which vector you take first. That's not the case for the cross product. So these two types of multiplication of vectors, in quotes, that word is a dangerous word, but these two operations, they do different things. The operation for the cross product is a little bit more complicated than that for the dot product. Okay. So we understand everything we need to know about how to take the cross product of unit vectors. So now we can shoot for the bigger picture. Namely, what happens if we want to take the cross product of friendly, pedestrian, ordinary vectors. So in particular, suppose I have a vector A, and I want to take the cross product of A with B. What is this thing? Well, if there are any mathematicians in the audience, this is the point when they get up and leave their offices or park benches respectively, screaming, because they must say something that's not rigorous at all mathematically. The answer to this quest is the result of calculating a determinant. So let me write out this determinant first, and second, let me tell you why the mathematicians should start leaving the room. If you take this determinant, this 3 by 3 object, you will get an answer that's called the cross product of A and B. This is really not a determinant, but we're going to treat it like a determinant. And the reason why it's not really a determinant is that I hat, j hat, and k hat are not scalars. They are vectors. So the elements of a matrix or a determinant are typically scalars. Having said that, if you go ahead and treat this thing as if it were a true determinant, you know that you would get an answer that looks like the following. I hat times a sub y times b sub z minus a sub z b sub y. So that's the first component. Second component would be j hat times a sub z b sub x minus a sub x b sub z. And you would get a third component, and she would be k hat times a sub x b sub y minus a sub y b sub x. So this thing looks horrendously complicated, but it is not. So the first thing I want you to do is show that that's actually the case. Multiply that out. Next, I want to show you or tell you that, in fact, this thing is something that you can write down immediately without having to go through the process of calculating this determinant, in quotes. Namely, recognize the following. I hat is a unit vector in the x direction, so let's call that 1. Y is sort of the second direction, that's 2, and z is the third direction, all using the cyclic rule, x, y, z. Then I have a minus sign in this term, and then I interchange the subscripts. So z becomes x, y becomes z, z becomes y. So it's minus a sub z times b sub y. So that's 1 down, 2 to go. The next term is j sub hat. Well, that's sort of 2, right? So the next guy is a sub z, that's 3, then b sub x, that's 1. Then I need my minus sign, and then I have a and b, they're fixed, they're left alone, but I interchange the subscripts. So z becomes x, x becomes z. And my final term goes like k hat, well, I associate that with the number 3. Here's a sub x, that's 1, b sub y, that's 2. Then I get a minus sign, and a and b are fixed, but I interchange the subscripts, a sub y, b sub x. So what I have done is use something called the cyclic rule to write down the determinant of vectors a and b very easily. The cyclic rule just says you go from 1 to 2 to 3 in that order, and once you get to 3, you go back to 1, 2, 3. So first term, 1, 2, 3. Second term, 2, 3, 1. Third term, 3, 1, 2. Okay. All right, so you can write, excuse me, actually you can write down the cross product of 2 ordinary vectors a and b 3 ways. One way is to write down this determinant, evaluate it formally. I've asked you to do that. The second way is just use the cyclic rule to write it down, which is easier. And the third way to, in fact, determine the cross product or vector product of 2 vectors is to, in fact, do the following. So all these methods are equivalent. They all should give you the same result. So the third way of calculating the cross product of A with B is to, in fact, write out these vectors in component form. I had A sub y, J hat, I'm sorry, I had A sub x, J hat A sub y, K hat A sub z. And I'll cross that into I hat B sub x plus J hat B sub y plus K hat B sub z. Now, since the cross product is distributive, what that means is that, excuse me, let's just take the cross product of A with the cross product of C added to D. This is just going to be the cross product of A with C plus the cross product of A with D. So what you will get formally when you evaluate this creature are that crossed into that, plus that crossed into that, plus that crossed into that. So what am I saying? You'll get 6 terms. You will get term 1 crossed into term 4, plus term 1 crossed into term 5, plus term 1 crossed into 2, 6. That's 3. 9 terms, sorry, not 6. Then you'll get 2 crossed into 4, plus 2 crossed into 5, plus 2 crossed into 6. That's an additional 3. That's 6. And then you'll add to that 3 crossed into 4, plus 3 crossed into 5, plus 3 crossed into 6. That's a final 3. 3 plus 3 plus 3 gives you 9. So you'll get your 9 terms. But it turns out that, and I was right actually, of those 9 terms, only 6 will be non-zero. There'll be 3 vanishing terms. So this is a way to evaluate this cross product, and you should show that this gives you the same result as before. Okay, let me say something that's sometimes not emphasized a lot. Because of this definition that we've introduced of the determinant, the cross product or the vector product only works, it only is defined if your vector is a vector in 3 dimensions. Otherwise, you don't know how to take those cross products, so that determinant doesn't mean anything. You know how to evaluate it. So the dot product or scalar product doesn't have that limitation. You can have a vector in 1 dimension, 2 dimensions, 3 dimensions, 10 dimensions, 39 dimensions for that matter. But if you want to take the cross product of 2 vectors or the vector product of 2 vectors, you can only do it those vectors are vectors in 3-dimensional coordinates. Okay, so this is all nice, and clearly the cross product and the vector product of vectors is far more complicated than the dot product of vectors. So I'm going to give you lots of opportunities in problem set 1 to practice playing around with vectors, vector multiplication, if you will, using dot product and cross products. But I would like to at least make an argument that the cross product of 2 vectors is a useful thing. So let's look at a useful application. And I'm not sure what I want to call this. The vector product or the cross product, both terms are synonymous. Let me just stop with vector product, leave it at that. But your audience will know which, doesn't matter which term you use. Cross product or vector product, your audience knows exactly what you're talking about, and they should know. So here's an interesting example. And again, I pull out my ruler. So let me take two vectors, and in fact, let me redraw that vector. So there's a little bit more interesting structure to it. Okay, so here's a vector. Here's another vector. So let's call this vector u. Let's call this vector v. Now let me take this vector u and just move it over. I don't change its direction, I just move it in space. So I form that, and I'll do the same thing with u. And so what I've constructed is something called a parallelogram. This is an object defined such that the opposite sides are parallel to each other. So side 1 is parallel to 2. Side 3 is parallel to 4. Okay, so I'm going to define my angle theta again. And now I'm going to do something a little bit more interesting. I'm going to realize that if I drop a line from this point so that it's perpendicular to this line here, and I can get rid of all these guys now. They've served the purpose. I know what they mean, so I don't need them anymore. This is a right triangle, and that's a right triangle. So this thing is a triangle here, and this is a triangle. Both of these guys, by inspection, have the same area. And then I'm left with a rectangle, not necessarily a square, it's a rectangle. So I want to ask myself, what is the area? What is the area of this parallelogram? Well, there's an easy way to figure that out. This parallelogram consists of two triangles and a rectangle. So the first question I want to ask is what is the area of this triangle over here? Triangle 1. So that just happens to be 1/2 the base of the triangle, which is the magnitude of v times the cosine. Let's do this in black, no reason to do this in red. 1/2 the magnitude of v times the cosine of theta, once I resolve v along the x-axis. And then the height is just v sine theta. So that's the area of one triangle. Triangle 2, or triangle number 1. Triangle number 2 is equivalent. So all I have to do is bring in a factor of 2 there. And then I just have to add the area of the rectangle. The rectangle has two sides. One side is going to be v sine theta. And you should look at that figure and make sure you believe that to be true. And the other side of the triangle is just going to be u minus v cosine theta. So I have some algebra to do. And I claim if I do this algebra, I discover that in fact, this result is just u v sine theta, or it's the magnitude of the cross product of the vector u with the vector v. So that's kind of neat. What it says is if you take a vector v and take a vector, or you take a vector u and take a vector v, and take the angle between them, starting from u and going to v, and form a parallelogram that's encapsulated or generated by those two vectors, that parallelogram has some area given by the illustrated lines or the shaded regime, and that area I know exactly what it is. It's just the norm of the cross product of u and v. And again, it doesn't matter whether I took the cross product of u and v or v and u, even though reversing that cross product gives you a minus sign. If I calculate the norm, let's do this a little better. It's a little sloppy. So this is going to be u v sine theta, which is just the norm of u crossed into v, which is equivalent to the norm of v crossed into u. So one possible application for a vector product is it's a way of telling you the area of the parallelogram generated by two vectors that are separated by an angle theta. Notice there's no need to bring in a unit normal vector here because I'm just talking about this magnitude. Later on, I will get into a subtle but important observation that area is also a vector. You may not be used to thinking of it as being a vector, but it is. So angles are vectors, and area can be looked at as an example of a vector. Okay, so I'm going to give you, as advertised, lots of practice with working through some of the concept most of the concept we've talked about today. Turns out that in science and engineering, there are tons of useful, excuse me, vector identities. Excuse me. Some of these you will actually prove in problem set 1. Let me just write a few of them down. Namely, the cross product of u, a vector u with a vector v, is minus the cross product of v with u. Another, I stated this before, but I didn't actually prove it, that the cross product is commutative. Namely, if you take the cross product of u with the sum of v and w, that's obviously equal to the cross product of u with the sum of w and v. So the addition of vectors is associative. And this is going to equal a cross product of u with v plus the cross product of u with w. I said associative. I probably will check that and come back to that, or you can check that in Google by saying that the addition of two vectors is associative. That's what I mean. And then finally, there is an important property of vectors that has a very easy way of me remembering what it is. If I take the cross product of these three vectors, I get our answer. Let me just write the answer down first. And this is the so-called back cab rule. and it's so important it gets its own little name. So I want to come back to this. I call this property the associative property of addition of vectors. I'm not 100% that's right. So you can send me an email message about it and prompt me and I can check it. But what we're trying to say here is A plus B gives the same result if you take B plus A. So this back cab rule can be remembered by this simple memory device, mnemonic back minus cab. And note the following. If you take the cross product of two vectors, you have to get a vector. So there's a vector on the left-hand side of this equation, there's a vector on the right-hand side of that equation. If you add two vectors together, you get a vector. If you take the cross product of a vector with a vector, you get a vector. And U cross V is a vector. You're adding that to U cross W, that's a vector. If you add two vectors together, you get a vector. So vector on the left-hand side must have a vector on the right-hand side. Is that true for the back cap rule? Yes. Cross product of two vectors B and C is a vector. If you take A and cross it into this vector B cross C, you must get a vector. So the structure you have on the right-hand side must correspond to a vector. A dot C is a scalar. The dot product of two vectors is a scalar. Scalar times a vector is a vector. So this first term on the left-hand side of the minus sign is a vector. The dot product of A and B is a scalar. You can take a scalar and multiply it by a vector, and you must get a vector. So all is true with all is well with the universe. A vector on the left-hand side equals a vector on the right-hand side minus a vector. So there are lots of other useful vector identities that I'm going to ask you to prove, and I'll leave that for problem set 1. And there are many. I mean, I thought about this the other day. There are probably at least 20 that I could write down. We're not going to use all of them, but we're going to use a lot of them. Okay, so let us summarize. Where we are. So we've talked about vectors. We've talked about the norm of vectors, how to calculate that. Creature. We've talked about how to resolve vectors into components. So all these very useful, important skills, the problem set 1 will show that you have a mastery of. Then we've talked about how to take the dot, well, even before we go there, we've introduced the idea of a unit vector. This is critical because it helps you build vectors. So maybe in fact, you probably talked about unit vectors way up front. We've talked about the scalar or dot product of two vectors. We've talked about the vector or cross product. Suspect that should be a small c of two vectors. As an example, we talked about the law of cosines. As an example, so that's an example of the dot product. And we've looked at a number of useful vector identities that you can use all of the above to prove. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I should point out that we've talked about this subject, or we reviewed this subject, almost exclusively from the point of view of Cartesian coordinates. And that's a very helpful and useful project to do. Turns out the Cartesian coordinates are nice, and they're nice in understanding physical problems, but there are a whole host of physical problems that if you really want to understand what's going on, you're going to have to use coordinate systems beyond Cartesian coordinate systems. You may have to use plane polar coordinates. You may have to use cylindrical polar coordinates. You may have to use spherical polar coordinates. And what we'll do next time, after you've had an opportunity to review problem set 1, spend some time going through it and looking at the solution key only when you've gotten stuck on some aspect of the problem. Don't go backwards, work forward. What we'll need to do next time is start looking at other coordinate systems, plane polar coordinates, cylindrical polar coordinates, and spherical polar coordinates. We'll take vectors, we'll take the concepts of unit vectors, we'll take the concept of dot product of vector, we'll take the concept of a cross product of vectors and apply those concepts to these other coordinate systems. But it's important to see how this works out in Cartesian coordinates first. 3-dimensional space, where we sort of have an easy or intuitive idea what's going on first. So we'll do that first, then we'll go on to plane polar coordinates, cylindrical polar coordinates, and ultimately spherical polar coordinates. These are not the only coordinate systems that exist, but these are the ones that we'll concern ourselves with in this course for a discussion of electricity and magnetism. Okay, that's the end of lecture 1. See you next week, a week from today, for lecture 2. Thank you.